All right, time for a video on covalent bonding. This will be the last of the videos for unit number 6. Covalent bonding is the second way in which atoms can satisfy the octet rule. Recall from the last video, the octet rule tells us that the most stable atoms have 8 valence electrons. There are a few exceptions to the octet rule. Those include hydrogen, helium, lithium, and beryllium. Those first 4 elements on the periodic table need only 2 valence electrons in order to become stable. But for the most part, it's 8. In ionic bonding, we exchanged electrons. A metal gave its electron away to a non-metal. The metal is losing their outermost energy level to find those 8 valence electrons. The non-metal filling up its outermost energy level to have its 8 valence electrons. In the case of covalent bonding, we share electrons. And there's a big difference between exchanging and sharing. At Christmas time, you might exchange a gift with a friend. When you exchange that gift, you don't expect to get it back. You don't ever think you'll get it back. It's permanent. It's a one-way street. Sharing, on the other hand, is a two-way process. If I have a CD that someone wants to borrow, I might share it with them. When I share that CD with them, I don't give up ownership. It's still my CD. I expect to get it back. It still belongs to me. In ionic bonding, it's a one-way transfer. The metal gives the electron to the non-metal. In covalent bonding, the sharing is mutual. One atom will share an electron with the other. That other atom will share an electron back. There's an electron coming from both atoms this time. For covalent bonding to occur, we need a special set of circumstances. For it to occur, you have to have atoms that have a strong grip on their electrons. We call it electronegativity. We need a high electronegativity. We need atoms that don't want to give them up. Because of that, metals cannot do covalent bonding. Metals have a very weak grip on their outermost electrons. They have what we say a very low electronegativity. So they're not going to get involved in the sharing process. They're just going to give them up. They're just going to give them away. For covalent bonding to occur, we need either nonmetals or metalloids for the process to happen. In most of the cases you're going to see nonmetals involved in the covalent bonding. Neither one of them want to give up the electrons, so what they're going to do instead is share those electrons. And I have 2 examples I want to talk you through. First involves hydrogen. This is a hydrogen atom. This is what a hydrogen atom might look like. In the outermost energy level, we have 1 valence electron. And we should come to expect that. It belongs to group 1. The elements in group 1 have 1 valence electron. Hydrogen is one of those exceptions to the octet rule, needing only 2 valence electrons to become stable. So what can happen is hydrogen can bump into another hydrogen atom. Hydrogen number 1 says, hey, I'll share an electron with you if you share an electron with me. And that is exactly what happens. They share their electrons with one another. And when they do so, this hydrogen can say it has 2 valence electrons. This hydrogen can say it has 2 valence electrons, making them both happy, making them both stable. The other example that I wanted to talk you through was water. This is one of the ones that we looked at in class. Again, these are our hydrogen atoms. Hydrogen has just 1 valence electron. We expect that of it because it belongs to group number 1. Again, it's an exception to the octet rule. It needs only 2 valence electrons to become stable. So each of these hydrogens are out to find 1 more. This is oxygen. And as you can see, I have 1, 2, 3, 4, 5, 6 valence electrons there. Again, that should not be a surprise to you by now. Oxygen is a member of group 16. Group 16 has 6 valence electrons. It does need 8 to become stable, so oxygen needs 2 more. So oxygen and hydrogen will come along. Oxygen will say, hey, let me borrow 1 of those electrons. I'll let you borrow 1 of mine. It does this with both hydrogen atoms. If hydrogen will let oxygen borrow its 1 electron, oxygen will let hydrogen borrow 1 of its 6. When it happens, when it takes place, when the covalent bonding occurs, hydrogen lets the oxygen use its electron. Again, hydrogen lets the oxygen use its electron. So we count up how many are actually around that oxygen atom now. 1, 2, 3, 4, 5, 6, 7, 8. It's an octet. It's stable. For our hydrogens, it's the same thing that happened over here. It has its one valence electron that is its own. It borrows one from the oxygen, so it can have two. Again, same story over here. Hydrogen has its one valence electron. It borrows one from the oxygen, so again it has two, making these hydrogen atoms just as stable as the oxygen. Notice though, when they do this, the hydrogen's electrons are still X's. The oxygen's electrons are still yellow dots. This is because they never give up ownership. That is still hydrogen's electron. That is still oxygen's electron. They are only sharing with each other. An ionic bond is defined as the force of attraction between oppositely charged ions. We don't have charges here, so we cannot define the covalent bond in the same way. Covalent bond is defined as a shared pair of electrons. This is the covalent bond, the shared pair of electrons. Now, because it's a very different kind of bonding and because it does not involve those ions, there are no positive and negative charges. The properties of the covalent substances are very different from the ionic ones. In those ionic substances, we have those strong electrical charges. So we have these strong forces of attraction between our particles. The positive and negative ions are all forming this network of electrical attraction, holding on to one another with very strong forces. Because of that strong force of attraction, ionic substances in general are solids at room temperature. And remember what we said about solids. The particles are stuck in fixed positions. We have strong attractive forces here that effectively sticks these particles in fixed positions. They make solids in general. Again, because of those strong forces of attraction, they have high melting points. You really have to speed these particles up to get them to break out of those fixed positions. Again, remember, melting is when we break the particles out of their fixed positions. If the forces holding them there are strong, they're going to have high melting points. Ionic substances have high boiling points as well. Again, recall, boiling occurs when we remove those attractive forces. If you've got strong forces here, it's going to take a lot of energy to remove them. And finally, they are hard. Think about biting into a chunk of rock salt. You break your teeth because it's so hard. Those strong attractive forces lock those particles in position, making them very hard substances. Very different story with the covalent substances. They have no strong charges holding them together. They don't have those strong forces of attraction. The forces are relatively weak in covalent substances. And because of that, we tend to see them as liquids and gases at room temperature, mostly gases. Think carbon dioxide here. The reason why carbon dioxide is a gas at room temperature is because there are no strong forces to lock the particles in the fixed positions. They have low melting point. It's easy to move them out of fixed positions if the forces that are holding them there are weak. Dry ice, which is frozen carbon dioxide, has a very low melting and boiling point. In fact, it sublimates because its melting and boiling points are so low. It jumps straight into the gas state because the forces of attraction are so weak between those particles. Think about water. Water is a liquid at room temperature, and the reason why it's a liquid at room temperature is because the attractive forces are relatively weak. It has a low melting point, 32 degrees Fahrenheit, 0 degrees Celsius, because of those weak forces. Something like table salt, on the other hand, where we're talking about thousands of degrees for a melting point, much, much higher because of much, much stronger forces. Water's boiling point, 100 degrees Celsius, 212 degrees Fahrenheit, is again much, much lower than table salts. And it's because of those weak forces of attraction. They are generally soft substances. Ice, It's crunchy, it's relatively hard, but much, much softer than table salt is. Plastics are covalent substances. They are much softer than things like table salt. Again, because of the lack of attractive forces. There are no charges there to hold these things together. And finally, another big difference between these ionic and covalent ones, because ionic substances have ions, positive and negative charges, they can conduct electricity, at least in their liquid phase. In their solid, those particles are getting locked in fixed positions. They can't move around very well. So something like solid table salt does not conduct electricity. But you melt it or you put it in a liquid phase by dissolving it in water, it conducts electricity very well. Covalent substances do not. Covalent substances don't have those electrical charges. They are neutral particles, so they do not conduct electricity. A very common misconception is to say that water conducts electricity. Water is covalent. Water does not conduct electricity. It lacks the charged particles that you need. So students say, Mr. Danko, if you take some water out of that sink and you use it to connect a circuit with a light bulb and a battery, the light bulb will light up. And I have to tell them, it's not the water that conducts the electricity. Tap water has ionic substances dissolved in it. It has salts dissolved in it. And it's those salts that conduct the electricity. If you did that exact same experiment with distilled water or pure water, the light bulb would not light up, because water is covalent and water does not conduct electricity. And not as much to say about the covalent ones as the ionic ones. General chemistry does involve more ionic substances than covalent ones. But as always the case, if you have any questions, please make sure to post them on the wall or ask me in class.